Something is orbiting a star 133 light-years away. It weighs 15 times as much as Jupiter. And by the rule everyone uses, that makes it a brown dwarf, a failed star, not a planet. Except the chemistry says otherwise. Webb looked at its atmosphere and found something unexpected. Kara measured the geometry of the system, and the orbit, the chemistry and the architecture all started pointing in the same direction, toward a world that may have grown inside a disk, not collapsed like a star. The number says one thing, the evidence says another. Tonight we're going to look at that object. 29 Cygni b, a companion sitting at the boundary between two categories, and carrying enough measurable clues that we can actually ask which side it belongs to. Because there are two very different ways to make something this massive. One builds from the bottom up. Dust becomes pebbles. Pebbles become cores. Gas falls in. A planet grows inside a disk, slowly over millions of years. The other begins more like a star. A cloud or a massive disk fragments under gravity. A clump collapses. A companion forms not from patient accumulation, but from a single gravitational event. Both routes can produce something this heavy. Both can leave it orbiting a star, but they don't leave the same fingerprints. By the end of tonight, we're going to look at those fingerprints, the 13 Jupiter rule, and why it was always softer than it sounded, what Webb found in the atmosphere, what the orbit remembers about this object's past, and whether the largest planets can cross a boundary we've been treating as final. If you enjoy exploring questions like this with us, subscribing helps others find them too. Sharing helps even more. Let's begin. There is a reason the public shorthand became so durable. It sounds as if it has the authority of physics behind it, and in one narrow sense it does. What made the threshold especially persuasive is that it arrived at the intersection of three different intuitions. First, people trusted that a physical process makes a better border than a historical story. Second, mass is measurable in ways formation history often is not. Third, the cosmos ought to reward us with a boundary simple enough to memorize. When those three intuitions converged around one number, the number inherited credibility much larger than the specific job it was asked to do. That matters for 29 Cygni b because it explains the emotional force of the shortcut. A viewer does not hear 13 Jupiter masses as one parameter among many. A viewer hears finality. A viewer hears that the object has crossed into another category by a kind of natural law. The case therefore begins not only with physics, but with the cultural afterlife of physics. We are dealing with a threshold that became persuasive because it felt clean in a universe that so often refuses to be clean. A Jupiter mass is the mass of the largest planet in our solar system, about 1.9 times 10 to the 27 kilograms. Stack enough of those together, and the pressure and temperature deep inside the object begin to change the story. At around 13 Jupiter masses, under a commonly cited set of assumptions, deuterium can fuse. Deuterium is a heavier isotope of hydrogen. It is much rarer than ordinary hydrogen, and it burns under less extreme conditions than the hydrogen fusion that powers stars. That makes the threshold feel serious. It marks a real shift in internal behavior. For a cold viewer meeting this topic for the first time, that sounds like the perfect dividing line. Below the threshold, planet. Above it, brown dwarf. A number, a mechanism, a clean border. It almost sounds unfair to ask for anything more. 29 Cygni b is the sort of companion that activates that instinct immediately. Early dynamical estimates placed it around 13.9 to 16.1 Jupiter masses. Later work summarized the mass as about 15 plus or minus 5 Jupiter masses. However you phrase it, the object sits right in the zone where the shortcut sounds decisive. If you were going to classify by number alone, this is the place to do it, but the number does something subtler. It tells you that deuterium burning may matter in the object's early thermal evolution. It does not tell you whether the object formed in a disk, accreted metal-rich material, emerged by fragmentation, or belongs to a low-mass stellar companion population. It gives you a regime, not a biography. That distinction is easy to miss because our words are carrying hidden assumptions. When people say planet in this borderland, they are often making an origin claim while pretending to make a mass claim. When they say brown dwarf, they are often doing the same thing in the opposite direction. The words look like labels, but they smuggle in a past tense. This is why the line feels more final than it really is. It is not only that 13 Jupiter masses sounds precise, it is that it sounds like it should answer every question at once. Physical process, historical pathway, identity, even public naming. The promise of a single threshold is that all those layers can be collapsed into one rule. Nature does not cooperate that neatly. One object can assemble in a disk and still become massive enough for partial deuterium burning. Another can arrive in the same mass range by a more fragmentation-driven route. If their histories differ but their final masses overlap, then the overlap itself becomes the important scientific fact. That is the first key move. We are not looking at an outlier. We are looking at an object inside the rule's most confident zone that still makes the rule feel insufficient. 29 Cygni B matters because the shortcut sounds strongest here. There is also a misunderstanding hidden in the phrase, almost a star. The threshold discussed is not the hydrogen fusion flaw that separates stars from non-stars. That flaw sits far higher, around 75 to 80 Jupiter masses. An object near 15 Jupiter masses is nowhere close to becoming a star. What people usually mean, without noticing, is that the object entered a substellar regime where limited deuterium burning can occur. That is narrower and more technical than popular language suggests. Once you say that plainly, the sense of inevitability starts to fade. Deuterium burning is interesting. It is not destiny. A brief interior process is not a complete description of identity. It does not erase system architecture. It does not erase chemistry. It does not erase the path by which gas and solids were assembled. It only tells us that the object's interior crossed one thermodynamic threshold. This is where 29 Cygni B shifts from a label problem to a forensic one. If mass only tells us that the object lives in a disputed regime, we need to ask what evidence still carries memory of origin after the mass has already been reached. That is a harder question. It is also the only question that can actually answer what kind of object this companion is. And once that need becomes obvious, the famous line starts looking less like a verdict and more like a historical convenience that outlived its own precision. The number sounds final, only because a long chain of scientific nuance was compressed into a sentence the wider world could remember. There is another reason the number became so sticky. It seems to offer fairness. If nature gives us a threshold tied to nuclear physics, then every newly discovered companion can be judged by the same rule. No one has to argue about whether the disk was massive enough, whether the orbit moved, whether the atmosphere still remembers the birth environment, or whether the host star changes the outcome. A threshold promises that the same sentence can be applied to every system in the sky. That universality is emotionally powerful, especially in a field where so much else is contingent. But the promise of fairness conceals a cost. Universal rules are tempting precisely where the underlying histories are least universal. The more diverse exoplanet systems became, the more the one-number rule began doing violence to that diversity. A hot Jupiter at a few hundredths of an astronomical unit, a wide, directly imaged companion at tens of astronomical units, and a free-floating substellar object in a young association can all occupy neighboring mass territory while emerging from very different environments. The threshold makes them look more similar than their histories really are. This is also why the language of crossing a line can mislead. Crossing sounds instantaneous, as if an object spends its growth history on one side of identity and then steps over into another. Real formation does not behave that way. A companion may pass through the deuterium burning regime after a long period of disk accretion that already gave it many of the properties we associate with giant planets. If so, the threshold is encountered during the story, not before the story. It is one event in the object's evolution, not the author of the object's entire nature. The boundary between planets, brown dwarfs, and stars was not discovered all at once. It was assembled in stages, and each stage answered a different question. That historical layering is easy to lose once later generations inherit a finished vocabulary. Terms like star, brown dwarf, and planet now sound as though they emerged from one coherent master theory. In reality, each label was stabilized under different observational pressures. Stellar theory matured first. Brown dwarfs were named in response to an expected substellar population. Exoplanet language expanded later under the pressure of new discoveries. By the time all three lanes began overlapping, the vocabulary was already carrying assumptions that had never been designed to meet one another cleanly. The oldest stable border in this story is the hydrogen-burning flaw. A star shines by sustaining hydrogen fusion in its interior. Below a certain mass, an object never reaches the core conditions needed to keep that process going. Long before exoplanets became part of everyday astronomy, theorists had already recognized that nature should produce bodies below the stellar threshold. They would not be ordinary stars, but they would not be planets in the familiar solar system sense either. By the mid-1970s, the term brown dwarf had become the accepted name for that substellar class. The name solved a language problem before it solved a classification problem. Astronomers needed a way to talk about bodies too small to sustain hydrogen fusion, yet more massive than the kinds of planets people already knew. At that stage, the category was anchored mostly in stellar theory. It was about what stars failed to become. That origin matters because it explains why the brown dwarf category was never designed with modern exoplanet diversity fully in mind. The category emerged before astronomers had long catalogues of hot Jupiters, super-Jupiters, directly imaged wide-orbit companions, and chemically characterized border objects around other stars. The language came first. The crowd of cases that would stress the language came later. The situation changed once exoplanet discoveries began to fill the lower mass end of the same broad territory. Giant planets, directly imaged companions, and faint substellar objects started piling up near the borderland between planetary and stellar language. What had once been a tidy gap became a crowded region of overlap. That is the setting for the 2002 Working Group on Extrasolar Planets of the International Astronomical Union. The group adopted an operational rule that used the deuterium burning limit, commonly quoted at about 13 Jupiter masses for solar-type composition, as a practical divider between planets and brown dwarfs. The value of that rule was obvious. It could be applied quickly. It gave catalogue makers a consistent standard. It offered observers a vocabulary for newly found companions whose formation histories were still uncertain. It made public explanation easy. Operational rules are not the same as deep truths, but science often needs operational rules. A telescope team cannot wait for philosophical perfection before naming what it found. Databases need columns. Press releases need one sentence. Review articles need a table. For a while, the deuterium threshold looked like a remarkably convenient compromise between physics and bookkeeping. That convenience had consequences. Once a rule becomes usable, it spreads beyond its original context. Students learn it, journalists repeat it. Popular science treats it as settled fact. Eventually, a working definition sounds like a natural law. That is what happened here. The formula was simple enough to survive translation from technical literature to public language without carrying much caution along. The caution mattered because the people using the rule professionally often understood its limits. A useful divider is not necessarily an ultimate divider. The deuterium threshold had always been a way of stabilizing discussion around a difficult borderland. It was never guaranteed to map cleanly onto formation history. It was never guaranteed to remain sharp under every composition. It was never guaranteed to capture what observers really wanted to know when they asked what kind of object a companion actually was. Even so, the rule became sticky because it solved three different social problems at once. It reduced ambiguity, it created comparability across discoveries, and it spared everyone from saying, each time, that the answer depended on a longer argument. There was also a subtler reason it spread so effectively. It fit the way modern astronomy often communicates with the public. Numbers are portable, histories are messy. You can put a mass in a headline. You cannot fit a careful account of disk chemistry, accretion timescales, and dynamical memory into one line without losing most of the audience. The deuterium shortcut was not only a scientific convenience, it was a communication convenience. Once that happened, the public started hearing a category verdict where astronomers had often intended only an operational placeholder. That difference is exactly why border cases now feel so jarring. The audience thinks a clean law is being violated. What is really happening is that an old convenience is being asked to do too much. 29 Cygni b arrives after 2 decades of that compression. That is why the case is so revealing. It does not only challenge a scientific shortcut, it challenges a habit of thought formed around the shortcut. The object sits where people expect the number to end the conversation, then presents a stack of evidence that forces the conversation back open. Once that happens, the question changes. We are no longer asking whether a working rule existed for good reasons. Of course it did. We are asking whether the rule ever deserved to be mistaken for the whole answer. And once theorists tested the underlying physics more carefully, even the neatness of the number itself began to soften. Institutional definitions tend to outlive their usefulness. The 2002 IAU rule addressed a field with a sparse, uneven exoplanet census. It made sense to choose a divider that could stabilize discussion while data were limited. But once observations recovered architecture, mass, and chemistry for border objects, freezing that early choice had costs. The definition was not foolish. It simply stopped scaling to the better evidence arriving. That is a general pattern in astronomy. Early categories are often shaped by what can be measured first, not by what will ultimately matter most. Spectral type came before stellar interiors were fully understood. Galaxy morphologies came before cosmological structure formation was described in modern detail. Planet brown dwarf language followed the same logic. Mass was easier to operationalize than formation history. What 29 Cygni b exposes is the moment when that early convenience starts colliding with richer evidence. Deuterium burning is real. It is worth saying that plainly, because criticism of the threshold is sometimes misheard as criticism of the physics. Deuterium is a heavy form of hydrogen with 1 proton and 1 neutron in its nucleus. Because of that extra neutron, it can fuse under less extreme conditions than ordinary hydrogen. In sufficiently massive substellar interiors, deuterium burning can begin even though the object is still far below the mass needed for long-lived hydrogen fusion. That is why the threshold attracted so much attention. It marks an authentic physical transition. The trouble begins when a real transition is turned into a universal taxonomic border. Physics gives us processes. Taxonomy tries to draw boxes around whole objects. Those are not the same activity. In detailed models, the mass at which deuterium burning becomes significant is not fixed at one number. Spiegel, Burrows, and Milsom explored how the threshold shifts with metallicity, helium fraction, initial deuterium abundance, and the chosen criterion for how much deuterium has to burn before one says the process mattered. Depending on the assumptions, the effective threshold can span roughly 11.0 to 16.3 Jupiter masses. That range matters because it breaks the illusion of a clean cliff edge. The public story sounds binary. The theoretical story looks more like a zone. If composition changes, the line moves. If the definition of significant deuterium burning changes, the line moves. If the object's internal conditions differ, the line moves. A supposedly simple border becomes contingent. Even that does not reach the deepest weakness. The deepest weakness is that the threshold answers a different question from the one people actually care about in cases like 29 Cygni b. Can the object burn some deuterium is a thermodynamic question. How did the object form is a historical question. The two are related, but nature does not promise that they align in a way that gives us one neat category boundary. A disk-built companion can grow massive enough to enter the deuterium-burning regime. A fragmentation-built companion can enter the same regime from another direction. If the mass domain overlaps, then burning deuterium cannot serve as identity paperwork all by itself. This is easier to see with a human analogy than with an astronomical one. Suppose two people end up the same height as adults. Height is real, it is measurable, it tells you something about their bodies, It does not tell you whether they had the same childhood, diet, training, or family history. A final number compresses many pathways into one outcome. Mass near 13 Jupiter masses behaves in a similar way. It can be the endpoint of more than one story. A useful way to think about this is to separate discovery language from explanatory language. Discovery language asks how we can group new objects quickly enough to talk about them. Explanatory language asks what physical history actually produced those objects. The deuterium threshold works well in the first register because it gives observers a regime to point to. It works badly in the second when people start using it as a substitute for origin. The border appears to fail only because we quietly switched questions without admitting it. Once that switch is noticed, the apparent confusion becomes more honest. We are not facing a mysterious contradiction in nature. We are facing a mismatch between the kind of border we wanted and the kind of evidence the universe is willing to provide. The universe offers overlapping pathways. We responded by drawing a cleaner line than the pathways warranted. There is a further complication. Deuterium burning is not a permanent identity trait. It is an episode in early evolution. Depending on mass and structure, an object may burn some fraction of its original deuterium supply and then cool onward into a later state that no longer advertises that brief phase in any simple way. If two objects share a present mass but had different accretion histories, internal entropies, or chemical compositions, their early burning histories can differ without giving us a clean everyday label decades later. Again, process is real. Classification is harder. 29 Cygni b is almost a perfect border object for exposing that fact, because it does not sit clearly above or below the disputed zone. It lives inside the zone, where the shortcut becomes least trustworthy. In one sense, that makes the classification harder. In another sense, it makes the scientific lesson cleaner. The threshold does not fail here because the object is badly measured. It fails here because the threshold is being asked to answer a question about origin that it was never designed to settle. Once that is clear, the rest of the case becomes easier to frame. We should not expect mass alone to settle identity. We should look for other clues that preserve memory of formation after the object has already reached its present state. Some clues survive in architecture. Some survive in chemistry. Some survive in the relation between the star and the companion. None of them is perfect. All of them are more relevant to origin than a mass threshold by itself. This is the real pivot in the story. 29 Cygni b stops being a naming annoyance and becomes a forensic test. The question is no longer which label sounds natural. The question is which formation history still fits once every available clue is put on the table. To do that honestly, we need to build the object itself into a proper case file. Even the meaning of significant deuterium burning is less obvious than casual language suggests. Does an object count as having crossed the line if it burns 10% of its original deuterium inventory? 50%? 90%? Different choices produce different thresholds, and none of those choices is handed down by nature as the uniquely correct taxonomic standard. They are modeling conventions attached to a real physical process. Once you see that, the elegance of the public number begins to look more like a negotiated summary than a discovered border. There is also an interesting pattern here. The very parameters that move the deuterium threshold, metallicity and helium fraction, are also linked to the environments where objects form. So the clean line is not only fuzzy, it is fuzzy in ways that already hint at formation context. The physics itself is quietly telling us that different birth environments can shift where the thermodynamic milestone appears. That should have been a warning from the start that the threshold could not serve as universal identity paperwork. And because deuterium burning is brief compared with the much longer cooling history of a substellar object, the process has an awkward relationship to observation. We often classify older companions long after the relevant burning episode is over, or largely over. We infer that the episode may have occurred from present mass and models, not from watching the burning directly. The famous line, therefore, feels more direct than it actually is. It is an inference about an early interior phase, used as if it were a present tense category label. 29 Cygni b is also referred to in the literature as HIP 99770b, after the catalogue number of its host star. The host star is an early type A star, roughly 40.7 parsecs away, a little over 130 light-years. That distance matters because it places the system close enough for multiple observing techniques to work together usefully. It is far enough away that we are not looking at a nearby solar system analogue in any simple sense, but close enough that astrometry, direct imaging, spectroscopy, and stellar interferometry can all contribute pieces of the same puzzle. The discovery path is one of the reasons this companion has such high evidentiary value. It did not appear first as a lone point in an image with almost no context. It emerged through astrometric acceleration. Hipparchos and Gaia, separated by decades, tracked the star's motion with enough precision to show that the path was not the smooth line expected for an isolated star. Something massive was tugging on it. That is already an important clue. Astrometry reveals that unseen mass is affecting the star's motion. When a directly imaged companion is found after that, the system becomes richer than a simple image alone. Position, brightness, and orbital geometry can be compared against the acceleration signal. Separate methods constrain the same object. Follow-up imaging with Subaru, including C-SAGSO and Caris, confirmed the companion. Direct imaging is never only about taking a picture. It matters because it opens the door to spectroscopy, atmosphere work, orbit tracing, and comparisons with other young substellar companions, whose light can also be separated from their stars. The projected orbital separation of 29 Cygni b is about 17 astronomical units. In everyday solar system terms, that is a little beyond the orbital scale of Uranus, and far inside the kind of enormous separations where some star-like companion scenarios feel immediately more comfortable. A companion at hundreds of astronomical units can often be discussed in a different demographic category from a companion at roughly 17 AU. That does not settle the matter, but it changes what kinds of histories feel plausible from the start. The mass ratio is another quiet but powerful clue. Relative to its host star, 29 Cygni b has a companion-to-star mass ratio on the order of 0.008 to 0.01. That low-Q architecture is not what we instinctively imagine when we think of a miniature stellar binary. Again, the clue is not decisive by itself. It is contextual. But context matters in border cases. Populations form patterns, and objects that belong to one population or another often carry those patterns in their ratios and separations long before anyone argues about labels. There is also the matter of the host star itself. An early type A star is not a sun-like star with slightly different branding. Higher mass stars can host more massive protoplanetary disks. They radiate differently. Their circumstellar environments shape growth conditions differently. If the question is how a companion near 15 Jupiter masses could plausibly be assembled in a disk, the host star context has to be part of the calculation. This is what made 29 Cygni b interesting even before the later chemistry work. It was already a directly imaged, low mass ratio, moderate separation companion near the deuterium burning line. In other words, it was already the sort of object that looked likely to tell us something important about where the old shorthand becomes unreliable. What changed in the next phase of study was not the basic mystery. What changed was the kind of evidence available to interrogate it. Once the atmosphere could be probed in a particularly informative infrared window, and once the orientation of the star's spin axis could be tied more tightly to the orbit of the companion, the system stopped being merely suggestive. It became a case in which mass, chemistry, geometry, and architecture could all be read against one another. That is rare enough to matter. Many classification arguments remain vague because one or two critical pieces of evidence are simply missing. Here, the object offered more than a number. It offered multiple partial memories of origin. Each of those memories comes from a different physical layer. Astrometry remembers gravity. Imaging remembers location and brightness. Spectroscopy remembers atmospheric composition. Interferometry remembers stellar geometry. None of those methods was designed as a planet or brown dwarf test in isolation. Together they become one. This is what gives 29 Cygni b unusual documentary strength. A lot of astronomical stories depend on one beautiful instrument result, and then spend the rest of the runtime protecting that result from overinterpretation. This story is stronger because no single observation has to carry the full burden. If one clue were weaker than hoped, the case would not collapse. It would merely become less sharp. That redundancy is exactly what you want when the broader question is about classification and origin. It also means we can ask finer questions than a simple discovery paper would permit. Is the object's low mass ratio more typical of planet-like companions than of stellar binaries? Does its moderate separation fit disk-built growth better than cloud fragmentation? Does the atmosphere look chemically like material processed inside a protoplanetary disk? Does the orbit look like it still remembers that disk? Each question is modest on its own. Together they become decisive. There is another quiet advantage in the way the case developed. The object was not introduced to the field through hype language about having solved a taxonomy problem. It entered as a measured companion near a famous threshold, then accumulated relevance as the evidence improved. That is the right order. The label controversy followed the data, not the other way around. For this reason, 29 Cygni b should not be imagined as a spectacular outlier detached from any broader population. It is better thought of as a particularly well-observed member of a difficult population. Its power comes from being legible. The object is not important because it breaks a record. It is important because we can actually interrogate it. And the strongest memory preserved in that interrogation came from the atmosphere. The star itself deserves more than a passing mention, because host stars are not neutral containers. An A-type star changes the entire background problem. Its higher mass means a stronger radiation field, a different disk temperature structure, and a different expectation for how much raw material may have been available while the system was young. Around a lower mass star, a companion near 15 Jupiter masses at this separation would often feel like a much harder sell for any planet-like pathway. Around an A star, the disk does not automatically make the verdict easy, but it does widen the corridor of plausibility. That matters because one of the quiet mistakes people make in classification debates is to imagine the companion in isolation, as if the star did not shape the supply lines, the chemistry, and the orbital environment from the start. Age matters in a similarly indirect way. Directly imaged companions are often interpreted through cooling models, and cooling models are only as useful as the age you feed into them. A younger object can look brighter at the same mass than an older one. A system with poorly constrained age therefore produces broad uncertainty in mass, temperature, and atmospheric interpretation. One reason 29 Cygni b is more useful than many border objects is that the evidentiary stack is not resting on brightness alone. The astrometric component helps with the mass, the imaging helps with location and photometry, the spectroscopy helps with chemistry, the stellar characterization helps with geometry. When several partial constraints overlap, the case does not depend on any single fragile assumption about age or evolutionary state. The discovery route also matters because Hipparchus and Gaia are not doing the same job as Subaru and JWST. Hipparchus and Gaia measure the star's motion on the sky to astonishing precision. If the star is being pulled by a companion, its path across the sky begins to curve or accelerate compared with the path a solitary star would take. That acceleration is not a pretty picture, but it is a deep piece of evidence. It says a hidden mass is present whether or not we have yet seen the companion directly. When Subaru later images a faint companion at the right place, we are not starting from zero, we are matching one line of evidence against another. The system becomes a solved geometry problem in stages. That layered method is one reason the mass estimate has more teeth than a pure brightness-derived estimate would have. In many direct imaging discoveries, the companion's mass begins life as a model-dependent inference from age and luminosity. Those estimates can be scientifically useful, but they are also easy targets in a classification fight, because a skeptic can always point to cooling assumptions and age ranges. Here the dynamical information from astrometric acceleration gives the mass estimate a firmer floor. It does not erase all uncertainty, but it narrows the zone in which hand-waving can survive. That is exactly what a boundary case needs. Even the orbital separation deserves to be unpacked more carefully than a simple number usually gets. 17 astronomical units sounds, to most people, either comfortably planetary because it recalls Uranus, or uncomfortably wide because it lies well beyond Jupiter and Saturn. In reality, it is neither simple. At that radius, the companion sits in a part of parameter space where disk-borne formation is demanding but not absurd, where the star's gravitational dominance is obvious, and where later dynamical reshaping could still have mattered without making the whole system look chaotic. It is a separation large enough to raise formation questions, but not so large that those questions immediately answer themselves in favor of fragmentation. Population comparisons sharpen that point. When astronomers look at stellar binaries, especially around more massive stars, they often see a different distribution in companion mass ratios than what 29 Cygni b shows. A companion with Q near 0.01 does not look like the most natural endpoint of ordinary binary star formation language. That does not mean binary-like roots are impossible. It means the demographics stop feeling like neutral ground for them. A low Q object at moderate separation already tilts the prior probabilities before chemistry says a word. There is a second demographic feature hidden inside direct imaging itself. Imaging tends to find what is bright and what is separated enough from the star to be resolved. That selection effect can mislead us if we treat every imaged companion as typical of one population or another. Some very wide, high-mass companions are found precisely because they are easier to separate from the host glare. Some closer-in, lower Q companions only enter the sample when the instrumentation becomes good enough. 29 Cygni b matters partly because it falls into the newer, harder regime, where the companions we recover are beginning to sample a less biased slice of the architecture we care about. In other words, the object is not only a scientific case file, it is also a sign that the observational frontier has moved to where the real overlap problem lives. This is why the evidence around the host star cannot be dismissed as scene setting. The star's rotation, the acceleration signal, the companion's projected separation, the mass ratio, and the imaging detections are all pieces of the same architecture. Once that architecture is assembled, the object stops looking like a free-floating classification puzzle and starts looking like a member of a system with a recoverable history. There is also something important in what the case file does not show. We are not dealing with a highly eccentric, obviously disturbed system in which violent scattering is the first explanation everyone reaches for. We are not dealing with a companion at hundreds of astronomical units where cloud fragmentation feels almost preloaded. We are not dealing with a mass ratio so high that the word binary would dominate every paragraph. The evidence is interesting precisely because the system stays moderate. It keeps inviting a planet-like reading without making that reading trivial. That combination, moderate separation, low mass ratio, direct imaging, astrometric leverage, and a host star capable of having supported a substantial disk, is why 29 Cygni b was already important before JWST chemistry entered the scene. The object was positioned to become a decisive test as soon as better atmospheric data arrived. It was not rescued into relevance by a later headline. It was waiting for the right evidence to reveal what kind of test it actually was. To see why chemistry matters so much in this story, it helps to begin with a simple principle. Atmospheres are not only what substellar objects wear on the outside. They are records of what those objects were built from, what processes shaped them, and how their interiors and envelopes evolved. For a long time, directly imaged companions were easier to detect than to diagnose. We could estimate luminosities, infer temperatures, and compare broad spectral behavior. But the deeper question of composition often remained frustratingly loose. That began to change when observing capability improved in the infrared, especially in the 4 to 5 micron range, where certain molecules become unusually informative. JWST gave 29 Cygni b a powerful new kind of scrutiny in that window. Around 4.3 microns, carbon dioxide features become relevant. Around 4.6 microns, carbon monoxide matters. Those bands are not merely decorative labels on a spectrum. They carry information about atmospheric chemistry, and through retrieval models they can help estimate metallicity, meaning the abundance of elements heavier than hydrogen and helium relative to a reference baseline. In the case of 29 Cygni b, that comparison becomes especially important because the baseline is the host star itself. If the companion appears enriched in heavy elements relative to the star, then the companion does not look like a simple miniature copy of stellar composition. It starts to look like an object that had access to metal-rich material during growth. That is exactly why the reported enrichment matters so much. Balmer and collaborators describe a metallicity ratio, Z sub b over Z sub star, of about 3 plus or minus 2. In plain language, the companion appears enriched relative to the star it orbits. The same interpretation points to a heavy element inventory equivalent to roughly 150 Earth masses. That is a striking number, and it deserves careful handling. It does not mean astronomers have weighed a literal rocky core hidden inside the companion. It means the atmosphere and modeling together point toward a substantial heavy element budget. The enrichment is not being inferred for spectacle. It is being inferred because the spectral data fit that kind of composition better than a simple stellar-like baseline. Why does that matter for formation? Because a classic expectation for giant planets formed in a protoplanetary disk is that they can become enriched by accreting solids and metal-rich gas during their assembly. A body that spends its growth history inside the chemistry of a disk can emerge with a composition that is meaningfully offset from the star's own bulk composition. A companion formed more like the low-mass end of a binary star system does not naturally begin with the same expectation. This is not a magic proof. Atmospheric retrievals depend on model assumptions. Clouds complicate interpretation. Temperature structure matters. Molecular abundances can be difficult to separate cleanly. The error bars are real. But strong evidence is not the same thing as perfect evidence. The important point is that the chemistry pushes in a specific direction. It is not neutral. That direction matters even more because the object is so massive. It would be easy to imagine that by the time a companion grows toward 15 Jupiter masses, any chemical signature of enriched assembly might be diluted beyond useful recognition. But 29 Cygni b suggests the opposite. The atmosphere still appears to carry origin-sensitive information. That means the upper edge of planet-like formation may remain chemically readable further upward than many people assumed. Comparison helps here. Other directly imaged planet-like companions, including members of the HR 8799 system, have made this same infrared lane scientifically rich. The point is not that 29 Cygni b must match them in every detail. The point is that enriched atmospheres have become part of an empirical pattern for at least some disk-built giant companions. That gives the chemistry context. It is not a one-off trick pulled from an unfamiliar spectrum. It belongs to a growing comparative language. There is also a methodological lesson worth pausing on. Mass is often treated as the hard data and chemistry as the interpretive layer. In cases like this, the hierarchy should almost be reversed. Mass tells us where the argument becomes difficult. Chemistry tells us which histories remain plausible. The more the field learns to retrieve atmospheres from directly imaged companions, the more composition starts functioning as evidence about origin, rather than as decorative detail. That shift matters for 29 Cygni b because the old shorthand is fundamentally blind to enrichment. The deuterium rule can tell you whether an object may have crossed a burning threshold. It cannot tell you whether the object's material was assembled in a solid, rich disk environment. The chemistry is answering the question the shortcut cannot even ask. Still, there are limits. Retrieval frameworks have priors. Cloud prescriptions matter. Disequilibrium chemistry can complicate inference. The star itself must be characterized well enough for the comparison to mean something. A careful verdict, therefore, cannot say chemistry proves the whole story. What it can say is that chemistry strongly disfavors a simple stellar-like reading and strongly supports a disk-built one. There is also the heavy element budget itself. About 150 Earth masses in heavy elements is not just a large number for effect. It tells us the object likely interacted with a substantial reservoir of non-primordial material. That is exactly the sort of memory we would expect from a giant companion assembled in a disk rich with solids and gas. It does not settle whether the route was extreme core accretion, some hybrid path, or a more complicated disk history. But it does make a compositionally bland miniature binary story harder to defend. In that sense, the chemistry is doing two jobs at once. It is pointing positively toward a disk-built history, and it is placing pressure on the rival idea that mass alone has already told us enough. Once you learn that the atmosphere appears enriched relative to the star, it becomes difficult to keep pretending the object is just a number in a table. The chemistry says something more consequential. It says the companion may retain a compositional fingerprint of disk-linked assembly, but chemistry is only one memory of origin. The orbit can preserve another, and in 29 Cygni b that second memory does not pull against the first. To understand why CO2 and CO matter, remember what retrieval does. Astronomers compare observed light across many wavelengths against models that include temperature, clouds, molecules, gravity, and pressure. A good fit does not give a direct ingredient list, it gives a probability picture of which conditions can reproduce the light. Retrievals are powerful but require humility. They are not arbitrary, but they depend on modeling choices. The 4 to 5 micron region is especially useful because it opens windows that are unusually sensitive to carbon chemistry in cool atmospheres. Carbon monoxide and carbon dioxide do not merely announce that carbon exists. Their relative strengths are shaped by temperature, pressure, vertical mixing, and elemental abundances. When a companion is observed there with enough quality, the spectrum starts behaving less like a general portrait and more like a chemical interrogation. In the case of 29 Cygni b, that interrogation matters because the resulting atmospheric picture is difficult to square with the idea of a composition that simply mirrors the host star. Metallicity in exoplanet science can sound abstract, so it is worth slowing down over what is actually being claimed. When astronomers say the companion appears metal-enriched, they mean that elements heavier than hydrogen and helium, carbon, oxygen, nitrogen, silicates, and the rest of the non-primordial inventory appear more abundant relative to a stellar baseline than a simple stellar copy model would predict. In the solar system, the giant planets are enriched relative to the Sun, and that pattern is one of the clues that giant planets did not condense as simple scaled-down stars. They formed in a disk that concentrated solids and processed gas. The details differ across systems, but the logic carries over. Enrichment is a memory of environmental processing. That is why the host star comparison is so valuable. A free-floating object with an enriched atmosphere would already be interesting, but it would be harder to anchor. Around 29 Cygni we have a reference composition in the star itself. The relevant question becomes not only what molecules are present in the companion, but whether the companion looks chemically like it was built from the same unprocessed reservoir as a stellar companion would be expected to be. The answer appears to be no, or at least not in any simple way. The object looks more metal-rich than the star. That pushes the interpretation toward a formation history that interacted with solid-rich disk material. The estimate of roughly 150 Earth masses in heavy elements is where the case becomes especially hard to ignore. Earth is about 6 times 10 to the 24 kilograms. Multiply that by 150 and you are talking about a non-trivial fraction of the entire heavy element budget expected in a young planetary system. Again, that number should not be visualized too literally as a clean buried core with a neat label on it. Giant companions mix, accrete, and evolve in complicated ways. But the number tells us the enrichment is not cosmetic. The atmospheric fit is pointing toward a growth history in which a great deal of non-primordial material mattered. That creates pressure on rival explanations in different ways. For a cloud fragmentation origin, the challenge is obvious. If the companion formed more like the low-mass end of a stellar binary, why is it not compositionally closer to the star? For disk instability, the question is subtler. A clump formed directly in the disk can still be called disk-built in a broad sense, but the route by which it becomes heavily enriched is not automatically straightforward. The companion may have to accrete solids efficiently, capture enriched material later, or inherit a part of the disk that was already chemically structured in a useful way. None of that is impossible. It simply means the chemistry is not passive background. It forces the models to work. There is also a larger comparative story hiding behind this single retrieval. For years, directly imaged companions were thought of as chemically blunt instruments. They were young, cloudy, and hard to characterize in detail. What JWST has changed is not the laws of formation, but the granularity with which atmospheres can now be read. The field is moving from broad temperature and luminosity descriptions toward composition-sensitive casework. 29 Cygni b matters because it lands exactly where that new capacity meets an old classification dispute. The atmosphere is not merely more detailed than before. It is detailed in the exact way the old mass shortcut failed to be. Another subtle point is that atmospheric composition is not only about what was accreted, but about what remained visible after formation. A very massive companion can, in principle, undergo enough mixing, contraction, and thermal evolution to blur simple chemical storytelling. If 29 Cygni b still shows an enrichment signal despite living near 15 Jupiter masses, that tells us something encouraging and inconvenient at the same time. Encouraging because origin-sensitive chemistry is still recoverable at the upper edge of giant planet-like masses. Inconvenient because it means the easy public story, high mass wipes out the planet reading, was weaker than many people realized. There is also the carbon chemistry itself. In cool atmospheres, Colorado and CO2 are shaped by equilibrium chemistry and vertical transport. Gas pulled upward from deeper layers can change what the upper atmosphere appears to contain. Clouds can suppress or reshape parts of the spectrum. The retrieval is not a certainty, it is a convergent model outcome where the data favor enrichment. The right phrasing is that the chemistry strongly supports a disk-built origin. The wrong phrasing would be that chemistry abolished all uncertainty. Even with that caution, the asymmetry remains important. If the chemistry were flatly neutral, the border debate would lean much harder on mass and architecture alone. Because the chemistry is not neutral, every rival pathway has to answer to it. That is the difference between a weak clue and a case-shaping clue. 29 Cygni b's atmosphere is case-shaping. The deepest consequence may be methodological. For a long time the field relied on mass, because mass was one of the few parameters that sounded objective enough to bear public classification. Atmospheres were treated as too soft, too model-dependent, or too incomplete to carry equal authority. The balance is beginning to change. In cases where the question is origin rather than interior thermodynamics, composition may now be the more relevant kind of evidence. That does not dethrone mass. It reassigns the jobs. Mass tells us when to investigate. Chemistry helps tells what we are investigating. Formation is not written only in composition. It can be written in architecture too, and that is often where origin becomes legible. A companion that grows within a protoplanetary disk begins life inside an organized structure of gas and dust that already has a preferred plane. Over time, the relation between the companion's orbit and the host star's spin axis can preserve part of that history. The memory is never perfect. Disks can warp, interactions can tilt or pump orbits, later perturbations can disturb what began aligned. But broad alignment still matters because it is easier to understand in a disk-linked history than in a strongly detached one. For 29 Cygni b, follow-up work using Chara helped constrain the host star's spin geometry, combined with the orbital information available for the companion, that made it possible to estimate the spin orbit offset. The result, about 12 plus or minus 6 degrees, is consistent with alignment at roughly the 2 sigma level. This is not a dramatic tabloid result, and that is one reason it is scientifically useful. A calm clue can be more valuable than a flashy one. If the system had turned out strongly misaligned, the case for a quiet disk-linked origin would have been placed under obvious pressure. Instead, the measured geometry sits comfortably within a picture in which the companion formed in the same broad disk environment that shaped the rest of the system. Restraint matters here. Alignment is not proof of a pristine disk history. Some fragmentation pathways can still leave systems that look aligned. Some disk-borne systems can later become misaligned. There is no single geometric signature that settles classification by itself. But border cases are rarely decided by a single clue. They are decided by whether multiple clues point coherently in the same direction or pull against each other. That is what makes the 29 Cygni b evidence stack compelling. Chemistry leans toward disk-built. Geometry supports it. Mass ratio does not reverse it. Separation does not undermine it. As more clues appear, the same story remains viable. There is a deeper reason alignment matters for the central question. The old shorthand was attractive because it reduced a three-dimensional problem to one scalar value. Geometry does the opposite. It reminds us that origin is often stored in relational facts rather than isolated ones. An object's identity is not only inside the object, it is partly in how the object sits within the system that produced it. This is one of the hidden difficulties in any attempt to classify massive companions with a single threshold. A threshold can tell you about interior burning conditions. It cannot tell you whether the orbit and the star remember a shared disk. It cannot tell you whether system architecture looks like the low mass ratio companion lane or the miniature binary lane. Those are precisely the kinds of clues that become more important once mass has stopped being enough. In practical terms, geometry turns the question from abstract taxonomy into system forensics. Did the star and companion emerge from a common organized plane, or does the system look more like a detached pairing? The answer is not absolute, but in this case it is directional. The system does not look like it is trying to escape a disk-linked reading. There is also value in the modest size of the measured offset. About 12 degrees is not perfect coplanarity, and that is part of what makes the measurement believable. Real disks are not idealized diagrams. Real systems experience torques, migration, and local perturbations. A small but non-zero offset can still be entirely compatible with a formation history anchored in a shared disk. If anything, the measurement reads more like astronomy than like a classroom picture. The geometry also interacts with the separation. At roughly 17 AU, we are not looking at a companion so wide that later capture-like narratives become tempting, nor so close that every orbital signature has been erased by extreme migration scenarios. The architecture feels like part of one system story rather than a mismatched appendage. Again, not proof, but in science, a history that keeps matching the texture of the evidence deserves increasing weight. By this point, the case has two independent memories of origin. The atmosphere points toward enrichment. The geometry remains consistent with disk-linked assembly. The mass ratio and orbital scale make the same family of stories plausible rather than absurd. That does not end the argument. It changes its structure. Instead of debating labels in the abstract, we can now ask a more disciplined question. If there are several ways to make a companion in this mass range, which ways survive the evidence best? Spin-orbit alignment is one of those pieces of evidence that sounds cleaner in a headline than it really is in nature. A perfectly flat disk around a perfectly isolated young star would tempt us to imagine that every body formed inside it should remain in the same plane forever. Real systems are less obedient. Young stars can interact with magnetic fields. Disks can warp under external torques. Growing companions can migrate, scatter, or perturb one another. Even the star's apparent spin orientation can be difficult to infer cleanly. So when alignment shows up in a real system, it should not be treated as a stamp of certainty. It should be treated as a clue about how much dynamical violence the system seems to remember. In the case of 29 Cygni b, that clue matters because the system does not appear to remember much violence at all. A spin-orbit offset of about 12 plus or minus 6 degrees leaves room for modest mismatch, but not for the kind of gross dislocation that would make a quiet disk-linked history feel implausible. If the companion had been produced through a strongly decoupled star-like route, or had experienced major later upheaval, a larger misalignment would have been easier to imagine. Instead, the geometry sits in a range that looks ordinary for a system that grew together and stayed broadly coherent. The Chara contribution is easy to underappreciate if you only think of interferometry as a niche technical specialty. In reality, long basiline optical interferometry is one of the few ways to recover fine information about stellar shape and orientation for nearby bright stars. Rapidly rotating A-stars are not perfect spheres. Their rotation can produce oblateness and gravity darkening, and those features carry information about how the star is oriented to us. Once that orientation is known with decent confidence, the companion's orbital plane can be compared against it. Suddenly a host star is no longer just a light source. It becomes part of the historical record. That relational aspect is important because formation categories are rarely stored in one variable. A companion may look ambiguous if you stare only at its mass. A system becomes less ambiguous when you ask whether the star, the orbit, and the atmosphere are all telling compatible stories. 29 Cygni b is persuasive because they are. The chemistry says enriched. The mass ratio says low Q. The geometry says broadly aligned. None of those clues rules alone. They form a coalition. There is a common objection worth addressing here. Could a fragmentation-built companion still end up aligned? Yes, in principle. Fragmentation is not a single cartoon process. If fragmentation happens in a flattened environment, or if later evolution damps some of the mismatch, alignment can survive. That possibility is real. But the question in this documentary is not whether a rival model can be made logically possible. It is whether that rival model remains the cleanest fit once all clues are considered together. Geometry does not make fragmentation impossible. It merely refuses to rescue it from the pressure created by chemistry and architecture. Alignment also matters for what it says about later system history. If 29 Cygni b had reached its present orbit only after a highly disruptive migration or scattering episode, we might expect more dynamical scar tissue. The current evidence does not advertise such a story. A moderate separation companion in rough alignment with the stellar spin axis reads more naturally as a body whose present architecture still remembers the disk it emerged from. That memory is exactly what the classification debate needs, because it gives us a route back from current observation to past assembly. There is also a scale issue that makes the geometry more informative than it might seem. At very small separations, tides and later dynamical processing can erase some of the original orbital memory. At extremely large separations, weak binding and wide orbit dynamics can complicate interpretation in a different direction. Around 17 astronomical units, 29 Cygni b lives in a middle regime where formation history is still legible without being completely overwritten by later extremes. That does not make the geometry unambiguous. It makes it worth taking seriously. The star's own nature reinforces that point. A-type stars spin rapidly and radiate strongly, which affects both their disks and how their orientations are measured. The fact that useful alignment information could still be extracted here is part of why this system is so valuable. Many border objects remain frustrating because one key dimension of evidence, chemistry, geometry, or mass, never becomes measurable enough to matter. 29 Cygni b is rare because multiple difficult dimensions were all brought into the same frame. Another reason geometry matters is psychological rather than purely physical. Public discussions about planet versus brown dwarf often treat the object as if it were a lonely body floating beside a star, carrying its identity entirely within itself. Orbital alignment reminds us that companions are system members. Their histories are partly external. The protoplanetary disk, the stellar spin, and the orbital plane are not accessories. They are the scaffolding of origin. Once you start thinking that way, it becomes much harder to believe that one interior burning threshold could ever have settled the whole matter. That shift in thinking is one of the most valuable things 29 Cygni b offers. The geometry does not merely support a disk-built interpretation. It teaches the viewer what kinds of evidence are actually worth trusting when a category border becomes fuzzy. Look for relational memory. Look for system architecture. Look for clues that remain attached to the object's past instead of only its present mass. At this point, it helps to separate the rival pathways cleanly, because borderland language becomes confusing very quickly if every route is allowed to blur into every other route. The first pathway is core accretion pushed toward the high mass edge. In this picture, solid material accumulates first, building a core that eventually becomes massive enough to trigger runaway gas accretion from the surrounding protoplanetary disk. This is the classic giant planet formation story in broad outline. It works well for a great deal of planetary thinking, but at the mass of 29 Cygni b, it becomes physically demanding. The disk must be massive, the timing must be favorable, the object has to keep accreting enormous amounts of gas before the disk disperses. And if the enrichment clue is real, the history must still preserve a meaningful heavy element signature after all that growth? That last part is important. High mass alone does not make core accretion impossible, but it does raise the burden of explanation. A disk around an early type A star may provide more material than a disk around a lower mass star. Even so, a companion approaching 15 Jupiter masses pushes us toward the outer envelope of what many people intuitively imagine a planet-building disk can do. That is exactly why 29 Cygni b is so interesting. It tests the ceiling, not the middle of the distribution. The second pathway is disk instability. Here the companion still forms inside the protoplanetary disk, but not by patiently building upward from solids in the standard bottom-up way. Instead, parts of a sufficiently massive and cool disk become gravitationally unstable and fragment into dense clumps. This matters because it prevents the story from collapsing disk-built into one exact mechanism. A body can be planet-like in origin without following the most textbook version of giant planet assembly. Disk instability is attractive in high-mass cases because it seems at first glance to solve the supply problem. If a massive disk can fragment directly, then very large companions no longer require such prolonged staged growth. But that convenience comes with its own questions. Under what conditions should such a clump survive? How much migration should follow? What chemical inheritance should be expected? And if enrichment is strong, how does the object acquire or preserve it? The third pathway is cloud or core fragmentation, the more star-like route. In this picture, the companion forms as part of the broader collapse and fragmentation process that also produces binary stars and multiple star systems. The companion is then better understood as the low-mass end of a stellar companion continuum, rather than as an extreme planet. This story often sits more naturally with higher mass ratios and more stellar-like chemical inheritance, though nature always makes room for exceptions at the edges. Once these routes are separated, the key question becomes what style of evidence each one would naturally predict. Core accretion pushed to the extreme would be most comfortable with a strong heavy element signature, because the object has had access to solid rich disk material during growth. It would be less comfortable with a chemistry that looked indistinguishable from the star. It also faces a resource problem. Can a disk around an early type A star supply enough mass and enough time to build such a large companion at roughly 17 astronomical units? The answer is not obviously no, but it requires conditions toward the generous end of what disks can provide. Disk instability is comfortable with the general idea of a disk origin and with producing massive companions more easily than slow core growth might. Its challenge is not mere mass. It is explaining why the object would emerge with the observed enrichment pattern if the enrichment really requires substantial capture of metal-rich material beyond a simpler stellar baseline. A disk instability route is not ruled out by the evidence, but it has to live inside that chemical pressure. Cloud fragmentation is attractive whenever mass gets high enough that people begin hearing echoes of the brown dwarf population. But the evidence has to match. A low mass ratio companion at moderate separation with enriched chemistry and disk-consistent alignment is not the most natural advertisement for a simple miniature binary interpretation. This route therefore serves as the baseline alternative that the case must defeat. These pathways are not simply different names for the same thing. They produce different expectations about what should remain visible after the fact. Core accretion expects disk processing. Disk instability expects disk birth, but not necessarily enrichment. Cloud fragmentation expects star-like chemistry. Clues matter because they are not neutral to those expectations. That is why the documentary cannot drift into a generic taxonomy lecture. The interesting disagreement is not a dictionary disagreement, it is a predictive disagreement. If you tell me how the object formed, you are also telling me what kinds of evidence should still be detectable in mass ratio, chemistry, separation, and alignment. The pathways matter because they let the data discriminate. There is also a population question running underneath the case. Companion surveys do not only find isolated objects, they reveal lanes. Some companions cluster in the demographic territory of stellar binaries, with higher mass ratios and different separation behavior. Others look more like the extreme tail of giant planet architectures. 29 Cygni b matters because its architecture does not sit comfortably in the stereotypical miniature binary lane, even before chemistry is added. This is where many conversations drift into confusion. Once a companion becomes massive, people treat planet and brown dwarf as mutually exclusive categories. But the real dispute is deeper. The meaningful divide is between formation histories, not labels. 29 Cygni b makes that distinction unavoidable. The companion may sit in a mass range often associated with brown dwarfs in public language. Yet the evidence is asking whether its origin was disk-built in a way more characteristic of giant planets. That is why the old vocabulary begins to creak. It was built to simplify the borderland, not to honor every mixed case inside it. Once the three pathways are on the table, the next step is to stop talking in principle and start asking a narrower question. In this specific system, with this specific evidence stack, which route is doing the least violence to the data? Core accretion at this mass range deserves more nuance than it usually gets in public science writing. The textbook version is easy to summarize. Build a solid core, cross a critical threshold, and gas falls in rapidly from the surrounding disk. But the upper edge is not just a scaled-up version of Jupiter's story. Once the envelope becomes massive, the rate of gas accretion can be set by what the disk can deliver, rather than by what the planet can internally process. Gap opening, thermal feedback, and the local viscosity of the disk all start mattering. In some models, very high masses are reachable if the disk is sufficiently rich and long-lived. In others, the object's own growth changes the disk structure in ways that throttle further supply. So when people say core accretion cannot make something like 29 Cygni b, they are often compressing a more technical argument about disk conditions into a slogan. That slogan becomes even shakier around an A-type star. More massive stars tend to host more massive disks, and more massive disks are exactly where the upper tail of planet-like formation becomes most interesting. The challenge is not simply whether enough gas exists in the abstract, it is whether the disk can both build and preserve the chemical story the atmosphere later seems to tell. A companion that ends up near 15 Jupiter masses, but still looks enriched relative to the star, is not just a gas giant stretched upward. It is a gas giant whose growth had to remain chemically selective, or at least chemically non-sterile. Disk instability, by contrast, changes which bottleneck appears first. If a sufficiently massive disk becomes gravitationally unstable, dense clumps can form more directly without waiting for long incremental core growth. That is why the mechanism is attractive whenever extreme masses enter the conversation. It offers a route around the timescale problem that haunts slow bottom-up assembly. But it brings its own discipline. Instability does not happen anywhere a theorist wants it to happen. The disk must cool efficiently enough, the mass distribution must be favorable, and the clump must survive migration and tidal disruption. In other words, disk instability solves some problems only by introducing others. It also complicates the language of identity in a revealing way. If 29 Cygni b formed by disk instability, would you call it a planet? Many astronomers would still be tempted to say yes in a broad disk-built sense, especially if the object remained low-Q and chemically processed. Others would hesitate because the mechanism feels less like the familiar planet-building story and more like a small-scale cousin of fragmentation. This is why the documentary has to keep saying planet-like rather than pretending the vocabulary is cleaner than it is. The meaningful question is not which word feels comforting, it is which family of histories best matches the evidence. Cloud, or core fragmentation, looks cleaner only because it postpones the hard questions. In that pathway, the companion forms more like a low-mass stellar partner during collapse of the natal cloud or its dense core. You no longer need to ask how a disk assembled an enormous companion before dispersal. You ask instead whether the resulting system architecture and chemistry look like the low-mass edge of binary formation. Sometimes they do. Very wide brown dwarf companions or systems with higher mass ratios often feel at home in that framework. But 29 Cygni b is not advertising itself that way. The more carefully the architecture is read, the less the miniature binary story seems like the default. Each pathway also predicts different kinds of scarcity. Extreme core accretion should be rare because it needs generous disks, favorable timing, and sustained growth. Disk instability should be rare because it needs disks that become unstable under the right thermal conditions and produce clumps that survive. Cloud fragmentation into such low mass ratios should be rare because binary-like formation more often populates other demographic regimes. Rare does not mean impossible. It means the object's demographic neighborhood becomes part of the evidence. When a system sits at the intersection of several rare pathways, the one requiring the fewest special rescues gains weight. There is also an observational asymmetry between the three models. A cloud fragmentation companion can be massive without being metal-enriched. A core accretion companion can be metal-enriched almost by design. Because disk processing supplies the heavy elements, a disk instability companion lives in the middle, capable in principle of sharing some disk-linked traits but not automatically expected to carry the same enrichment signature. That is why chemistry does not only rank the models after the fact, it changes how we think about what each pathway would have had to do. This is also where the phrase brown dwarf becomes least helpful. Brown dwarf can refer to an interior regime, a mass shorthand, a formation intuition, or a survey category, depending on who is speaking. Those uses are not identical. A fragmentation-built substellar companion can be called a brown dwarf in one meaningful sense. A disk-built companion that briefly burns deuterium can also be called a brown dwarf in another sense, if a catalogue adopts the mass rule. The category confusion is real because the word is being asked to cover multiple scientific questions at once. 29 Cygni b is hard to discuss precisely because the most interesting answer is formation-based, while the public vocabulary is mostly mass-based. The honest way to proceed is therefore comparative rather than doctrinal. Do not start from a preferred word and bend the object into it. Start from the available evidence and ask which mechanism seems least strained. Does the architecture look like a low-mass binary? Does the chemistry look like star-like inheritance? Does the alignment look disconnected from a disk? If the answer keeps coming back no, then the rival route remains possible only in a technical sense. Science can live with that. Public shorthand usually cannot. Another useful distinction is between broad family and exact mechanism. The broad family question is whether the object formed within the circumstellar disk or in a more star-like fragmentation channel. The exact mechanism question is whether that disk-based origin was classical core accretion, some enriched variant, disk instability followed by later processing, or a hybrid story not cleanly captured by textbooks. 29 Cygni b lets us answer the broad family question more strongly than the exact mechanism question. That is not a weakness. It is the level of precision the evidence genuinely supports. A disciplined verdict begins by asking which story is under the greatest strain. The simplest cloud fragmentation reading, treating 29 Cygni b as essentially the low-mass tail of a stellar companion population, struggles first. The low companion-to-star mass ratio is not impossible for that picture, but it is not its most comfortable terrain. The orbital separation at around 17 astronomical units does not rescue the model by default. Most importantly, the atmospheric enrichment relative to the host star becomes awkward. If the companion inherited composition in a broadly stellar way, why does it appear enriched in heavy elements relative to the star it orbits? A defender of cloud fragmentation can propose extra steps, but the story becomes less economical. That matters because good scientific interpretation is not only about whether a model can be saved with enough auxiliary explanation, it is also about whether the model remains the best fit once all the clues are considered together. Here the chemistry does real work. It does not merely decorate the case, it places a burden on any star-like origin story. Disk instability deserves more respect, because it remains a disk-based route and can in principle produce massive companions more easily than an extreme version of core accretion. If the case ended with mass and orbital scale alone, disk instability would be a strong rival. Even with the chemistry added, it remains the most serious alternative inside the broad disk-built family. But the same chemistry that weakens cloud fragmentation also creates pressure here. If the companion's atmosphere really reflects significant heavy element enrichment, then the best-fitting history may involve not only birth in a disk, but also substantial access to metal-rich material during growth. That pushes the interpretation toward a more accretion-rich planet-like history, even if every mechanistic detail is not fully nailed down. This is why the narrow verdict has to be worded carefully. The evidence most strongly favors a disk-built, planet-like origin for 29 Cygni b. That wording leaves room for uncertainty about the exact route, while still ranking the broad families honestly. It says the companion is better understood through the logic of giant planet formation in a protoplanetary disk than through the logic of a simple star-like companion pathway. The geometry helps because it removes one obvious objection. A strongly misaligned orbit could have forced much more hesitation. Instead, the measured spin-orbit difference remains consistent with alignment. That does not prove a quiet history, but it does mean the system is not pushing back hard against a disk-linked interpretation. The host star environment matters too. Around an early Type A star, the idea of a more massive protoplanetary disk is not a wild convenience invented to save the argument. It is part of the physical context. If any systems are likely to stretch the upper mass scale of disk-built companions, such systems are among the plausible candidates. By this point, the evidence stack reads coherently. The mass tells us the case belongs in the disputed zone. The architecture says low-Q companion. The chemistry says enrichment relative to the host star. The geometry remains disconsistent. No single clue carries the whole verdict. Together they lean in the same direction. This is the crucial reversal in the documentary. If you begin from the public shortcut, 29 Cygni b sounds almost automatically like a brown dwarf. Once the formation evidence is allowed into the room, the object looks different. The same mass that once felt decisive becomes the least decisive part of the file. That sentence is worth lingering on because it captures the deeper methodological lesson. Mass is not useless. It is simply coarse. It tells us which companions deserve special scrutiny. It rarely tells us which origin story won. In this case, the closer you move to the evidence most sensitive to origin, the more the verdict shifts away from the public expectation. There is also the issue of asymmetry. We do not need every rival model to be impossible before we can rank them. Science often works by degrees of strain. One model explains the data with fewer extra assumptions, fewer exceptions, and fewer special rescues. Another can survive, but only by becoming increasingly baroque. 29 Cygni b is one of those cases. The star-like reading can be defended in principle. It is simply not the cleanest explanation of the evidence we have. That does not solve every mechanistic detail. It does not prove that one textbook formation channel operated exactly as drawn on a whiteboard. It does not settle the taxonomy of every similar companion, but it does support a strong, narrow answer to the case at hand. Under current evidence, 29 Cygni b is best interpreted as a disk-built, planet-like companion. What the case has not done is settle the broader question of how high disk-built companions can really go. In fact, the case makes that broader question harder to avoid. A good way to test the rival stories is to ask what each one has to explain away. Start with cloud fragmentation. It does not have trouble making a substellar object in this mass range. It does have trouble making that object look chemically enriched relative to the host star, remain in a low mass ratio architecture, and sit in broad spin-orbit alignment without the system feeling like a miniature binary. A defender can respond that rare fragmentation outcomes exist, and that chemistry may yet be revised. All true, but those replies function as escape hatches, not as reasons to prefer the model. And take disk instability. This route gets a great deal of mileage from the host star context. A more massive star can support a more massive disk, and a massive disk makes the instability route easier to imagine. The moderate separation does not kill it. The low mass ratio does not kill it. The alignment is perfectly comfortable for it. The chemistry is where the pressure concentrates. If 29 Cygni b really is enriched to the degree the retrieval suggests, then a simple direct clump story begins to feel incomplete. The model can survive only by absorbing extra processing, extra solid capture, or some disk chemistry structure strong enough to mimic a more accretion-rich history. That does not make disk instability a straw man. In fact, the seriousness of this alternative is one reason the final verdict must stay disciplined. If the evidence only had to defeat cloud fragmentation, the conclusion would be easier and perhaps less interesting. The case is scientifically richer because the strongest broad verdict is disk-built, while the most exact mechanism inside that family remains open to debate. The object is telling us more about the family than about the precise recipe. This is why the phrase rapid accretion of metal-rich material is so useful. It captures the part of the story the atmosphere seems to remember, without pretending we have watched every stage of assembly. It says the companion likely interacted with enriched disk material in a significant way. It does not insist that we have pinned that interaction to one single formation cartoon. In evidence-led science, that kind of phrasing is often stronger than a bolder sentence would be, because it matches what the data truly constrain. Another way to see the ranking is to ask how surprising the evidence would be under each model. Under a star-like fragmentation model, strong enrichment relative to the host is surprising. Under a broad disk-built model, enrichment is expected, or at least unsurprising. Under a cloud fragmentation picture, low-Q architecture is less comfortable than under a planet-like one. Under a disk-built picture, broad alignment is unsurprising. When several pieces of evidence keep landing in the unsurprising column for one family and the surprising column for another, the rational response is not to demand impossibility. It is to update the ranking. The case also benefits from what is sometimes called consilience, the way different kinds of evidence independently point toward the same explanation. The mass estimate comes from dynamical and imaging information. The chemistry comes from infrared spectroscopy and retrieval models. The alignment comes from interferometric stellar characterization plus orbital inference. These are not redundant measurements of the same thing. They are different windows onto the system. When they converge, the explanation they converge on becomes more credible precisely because no single systematic error needs to be carrying the whole conclusion. That convergence does something important to the emotional structure of the argument. The viewer began with the expectation that a number should settle the case. The case now ends with the realization that the number was the least informative clue once the richer evidence arrived. That is not a rhetorical trick. It is the actual order of relevance. The more origin-sensitive the evidence becomes, the less the mass-only shortcut dominates. A careful verdict should therefore sound like this: 29 Cygni b is best interpreted as a disk-built, planet-like companion. The present evidence is most consistent with formation within a protoplanetary disk and substantial accretion of metal-rich material. A star-like fragmentation origin is the weakest fit. Disk instability remains the strongest exact mechanism alternative within the broad disk family, but it sits under chemical pressure that keeps a more enrichment-driven planet-like reading in front. Notice what that verdict does not say. It does not say the taxonomy problem is solved for every object near 13 Jupiter masses. It does not say all companions above the deuterium-burning line are planets in disguise. It does not say every enriched atmosphere proves core accretion in a narrow textbook sense. It says the case file at hand has a best reading, and that best reading is not the one the public shortcut would have led you to expect. That is why this object matters so much. It is not merely a border object. It is a border object with enough independent evidence to force a ranking of histories. Plenty of companions make the old rule look awkward. Fewer companions make it look scientifically secondary. 29 Cygni b belongs to that smaller set. Once 29 Cygni b is interpreted as disk-built in the broad, planet-like sense, the boundary problem shifts upward. That upward shift is important because it changes the meaning of the case. At the beginning, the story sounds like it might be about rescuing one object from the wrong label. By this point, it has become a limit problem. If disk-built formation can plausibly reach deeper into the old brown dwarf zone than public language allowed, then the border problem is not a niche problem. It is a sign that the upper end of giant planet formation has been under-described. The first constraint is simple mass budget. A giant companion cannot accrete gas that never existed in the disk. If a system is going to produce a body near 15 Jupiter masses, the surrounding disk must have been correspondingly generous, and generous enough in the right region of the system to sustain continued growth. That is why the host star matters so much. Early Type A stars can host more massive disks than lower mass stars. The disk environment is not a scaled copy of the young solar system. The supply conditions can be meaningfully different. The second constraint is time. Protoplanetary disks do not last forever. Gas disperses, radiation and stellar winds reshape the system. Accretion has only a limited window in which it can proceed efficiently. Building a companion to several Jupiter masses is already a race. Building one toward the neighborhood of 15 Jupiter masses is a harder race still. The third constraint is location. At around 17 astronomical units, 29 Cygni b occupies a region that is neither so close to the star that classical hot planet intuitions apply, nor so far away that wide separation fragmentation language becomes the default. Growth conditions, migration possibilities, and thermal history all depend on where in the disk the relevant accretion took place. The present orbit may or may not be the full story of where the companion assembled, but the orbital scale remains part of the plausibility test. The fourth constraint is cooling. A growing giant companion has to shed heat if it is going to continue accreting efficiently. Thermal physics can throttle growth. The more massive the object becomes, the more its luminosity and contraction history begin affecting what kind of additional material it can pull in and retain. This is one reason the upper edge of giant planet formation is not just a counting problem, it is a thermodynamic one. Then there is the compositional challenge, and this is where 29 Cygni b becomes especially instructive. It is one thing to imagine a very massive companion assembling in a gas-rich environment. It is another to imagine that companion still carrying an atmospheric signature that appears enriched relative to the star. Growth alone is not enough. The growth has to remain chemically legible. That legibility matters because it hints that the upper edge of planet-like formation may not simply be a region where every object becomes compositionally bland. If enrichment survives at these masses, then disks are not only capable of building large companions, they may also leave behind evidence of how they did it. There is also a conceptual constraint worth naming directly. Public language treats 13 Jupiter masses as if it were the place where planets stop because the number is high enough to feel naturally terminal. But physical processes do not respect our feeling for where a story ought to end. If a disk around a suitable star can supply enough material quickly enough, then nothing about a famous public threshold prevents a disk-built object from living on the far side of it. This is one of the ways 29 Cygni b demotes the old shortcut rather than merely challenging it. The object does not only show that one companion can be argued over, it shows that the real upper edge of disk-built formation is itself an open research problem. The threshold is no longer an answer, it is a prompt. There are practical ceilings, of course. A disk too low in mass cannot do the job. A disk that disperses too quickly cannot do the job. A growth pathway that destroys its own enrichment signal may not match what is observed. Migration can either help by moving material into reach or hinder by destabilizing the architecture. Cooling rates can permit continued accretion or choke it. All of these are boundary-making processes. None of them is captured by one public number. This is where the host star context returns with force. Around Sun-like stars, a 15 Jupiter mass disk-built companion at moderate separation may already sound extreme. Around an A-type star, with access to a more massive primordial disk, the possibility becomes easier to entertain. That does not make it ordinary. It does make it physically discussable without special pleading. Another reason this matters is comparative. If 29 Cygni b were the only object pushing this upper territory, the story would remain more tentative. But the field has spent years accumulating hints that very massive companions can still look architecturally and chemically planet-like. Not all of them tell the story as cleanly. This one simply forces the question with unusual sharpness. That is why the broader lesson is not that disks can make anything. Somewhere the budget, timescale, and thermal constraints win. Somewhere the object begins looking more naturally like another population. But the scientific question is now about where those real limits lie. Not about preserving a public rule because it once sounded clean. There is still one risk in talking this way. The viewer could hear the argument and think 29 Cygni b must therefore be a completely isolated oddity. It is not. Comparison objects show that the pattern is broader, even if this case is especially sharp. That is why a few carefully chosen comparisons matter next. The upper limit problem is harder than it first appears, because several ceilings can intervene before a disk runs out of material in the simplest sense. One ceiling is gap opening. As a growing giant companion becomes massive, it can carve a gap in the disk and begin regulating its own supply. Gas can still cross the gap under some conditions, but the geometry of inflow changes. The companion is no longer merely a passive sink at the end of a pipeline. It becomes an active perturber of the very reservoir feeding it. Any argument about how high planet-like growth can go, therefore, has to ask not just how much gas existed, but how the disk-companion interaction evolved as the companion became large enough to reshape the disk. A second ceiling is feedback from the companion itself. Accretion releases energy. A luminous growing object heats its local environment and changes the thermodynamics of further inflow. In some models, that feedback can slow accretion or alter how gas and solids are delivered. This is one reason upper mass outcomes are not a simple extrapolation of smaller ones. The object being built changes the conditions under which additional mass can be built. A third ceiling concerns solids. The atmosphere of 29 Cygni b appears enriched, which implies that whatever disk-based process operated did not merely pour in hydrogen and helium from a chemically bland reservoir. Solid-rich material or metal-enriched gas had to matter, yet as a companion grows more massive, one might expect dilution to become severe. The heavy element signal could be washed out by the sheer quantity of nebular gas involved. If enrichment survives, as it appears to here, then either the supply of heavy elements was substantial, the timing favored their retention, or the disk environment remained chemically structured enough for the signature not to vanish. That is a stronger constraint than mass budget alone. Migration complicates the picture further. A companion does not necessarily assemble exactly where we see it now. Disk torques can move giant bodies inward or outward, depending on local conditions, disk structure, and the evolving mass of the object. If 29 Cygni b formed farther out, migration may have brought it inward toward its current location. If it formed closer in, some outward movement or scattering-like history would have to be considered. Every migration history changes what material was available and how long accretion could continue. So when we ask how a disk-built companion reaches roughly 15 Jupiter masses at around 17 astronomical units, we are really asking about a moving target inside a changing disk. Cooling time enters because accretion and contraction are coupled. A giant companion that cannot lose heat efficiently builds pressure support that resists further compression. A companion that cools more effectively can continue contracting and remain open to additional mass growth. This is one of the least intuitive parts of the problem for a general audience, because it means the upper mass ceiling depends not only on how much matter is nearby, but on how the growing object sheds the energy of becoming itself. Host star mass now returns as more than a convenience. Around an A-type star, larger disk masses and perhaps different temperature structures can move several of these ceilings at once. More gas may be available. The disk's gravitational behavior may differ. The radial zones in which cooling and instability matter may shift. This does not mean early-type systems can effortlessly manufacture giant companions of any mass. It means the plausible upper envelope for disk-built outcomes is not universal across stellar types. A number that feels high around the Sun does not automatically feel equally high around a more massive star. This is why 29 Cygni b is such a good stress test. It is not only that the object exists, it is that it exists in a host environment where pushing the upper tail of disk-built formation is physically discussable, and it still appears to preserve chemical evidence of that route. That combination forces theorists to take the upper edge seriously, rather than dismissing it as a semantic loophole. There is a broader theoretical consequence here. The traditional 13 Jupiter mass divider encouraged a kind of intellectual laziness at the top end of planet formation. Once a companion crossed the shortcut, public conversation often stopped asking whether disks could really have made it. The object was simply moved into another bin. Cases like 29 Cygni b reopen that suspended question. The real issue is not whether a famous number has been crossed. The real issue is where disk physics, accretion physics, cooling physics, and compositional memory actually fail. That is a more demanding question, and it may not have one single answer. The upper limit could depend on host star mass, disk metallicity, disk lifetime, orbital location, and the details of how solids are delivered. In some systems, the disk-built ceiling may lie comfortably below the deuterium burning regime. In others, it may intrude into it. In a few extreme systems, it may pass through it decisively. The important point is that the ceiling is environmental, not universal. This is also why the wider taxonomy problem will remain alive even if 29 Cygni b is read correctly. Overlap is not a bug. It is what happens when different formation channels populate the same mass territory under different conditions. A single public boundary was always going to crack once the field accumulated enough objects in that overlap zone. The real achievement of a case like this is that it shows where the meaningful physical limits have to be searched for instead. One final constraint deserves attention, and it is the constraint of comparison with the solar system itself. Jupiter, for all its importance, is a poor intuitive guide to the upper edge of planet formation around more massive stars. If we keep treating our own system as the default template, objects like 29 Cygni b will always look like violations rather than tests. But planetary systems do not scale in such a simple way. Different stars seed different disks with different masses, lifetimes, and thermal structures. The ceiling implied by Jupiter is therefore a local ceiling, not a cosmic one. 29 Cygni b forces the viewer to let go of that solar system reflex. It also forces a distinction between rarity and impossibility. A 15 Jupiter mass disk-built companion may be rare even in favorable systems. Rarity is exactly what we should expect near a physical ceiling. Outcomes thin out before they disappear. If that is the regime 29 Cygni b occupies, then its existence is not an embarrassment to theory. It is a clue about where the tail of the distribution may actually run. What matters is whether the evidence around the object still looks like the tail of planet-like formation, or the beginning of a different population. In this case, the evidence keeps pulling toward the first reading. Comparison objects are useful only when they sharpen the main case, instead of pulling the story away from it. The first comparison worth making is to the HR 8799 system. Those directly imaged planets became iconic long before JWST, but the reason they matter here is specific. Observations in the same broad 4 to 5 micron chemistry lane have made the atmospheres of those companions newly informative, especially where carbon-bearing molecules help distinguish composition and formation context. The point is not that HR 8799 and 29 Cygni are twins. They are not. The point is that enriched atmospheres in directly imaged planet-like companions are not an isolated conceptual trick invented for one object. There is an empirical lane in which chemistry has become a serious formation clue. That matters because it prevents 29 Cygni b from being framed as a special pleading case. If similar observing strategies are helping reveal chemically meaningful differences in other directly imaged giant companions, then the inference here belongs to a broader methodological shift. The field is learning to read formation clues from atmospheres more confidently than it could a decade earlier. The second comparison pushes in the opposite direction. A benchmark object such as HD 19467b is useful not because it shares every trait with 29 Cygni b, but because it occupies the same general observational terrain while pointing toward a different interpretive lane. Similar wavelength coverage does not force similar formation conclusions. Chemistry can distinguish. That is exactly the point. The same instrument class and the same spectral region can illuminate why one companion looks more planet-like, while another fits more comfortably into a brown dwarf framework. This is important for another reason. It shows that the argument is not stacked in favor of one conclusion by the method itself. We are not using a tool that automatically turns every massive companion into a planet-like object. The method can support different outcomes. That gives the 29 Cygni b verdict more credibility. A brief third comparison is Beta Pictoris b. This object is often invoked lazily in public discussion as if it were only another example of a very massive planet. The better reason to mention it is narrower. Beta Pictoris b reminds us that high mass alone never guaranteed a brown dwarf reading when the rest of the system evidence pushed elsewhere. The point is not to litigate that system in detail. It is to show that the intuition mass equals brown dwarf has been under pressure for years, even before 29 Cygni b brought a particularly sharp, chemistry plus geometry case into view. Seen together, these comparisons do not turn 29 Cygni b into a generic member of a crowded class. They do something more useful. They show that similar masses can belong to different stories. The overlap is real. The methods for distinguishing those stories are improving. And 29 Cygni b stands out because it sits so close to the famous public boundary while still preserving a coherent stack of origin-sensitive clues. There is also a strategic reason to keep the comparisons short. The more time we spend away from 29 Cygni b, the easier it becomes to retreat into generalities. But the force of the argument comes from staying with the one object that most directly embarrasses the mass-only shortcut. The comparisons are there only to show that the method has context and that the verdict is not an isolated whim. Used correctly, they also reveal something broader about how astronomical categories change. Categories rarely collapse because one object proves them wrong in a dramatic single blow. More often, the field accumulates a set of cases that make the old language steadily less adequate. HR 8799 helped show that atmospheres can preserve origin-sensitive enrichment. HD 19467b helps show that the same observational lane can support a different outcome. Beta Pictoris b helped normalize the idea that very high mass does not overrule every other clue. 29 Cygni b becomes powerful because it sits where all of those lessons converge. That is why this object matters beyond its own system. It does not simply produce a local exception to a rule. It exposes the cost of confusing mass categories with formation categories across the whole borderland. Once the viewer sees that chemistry can separate companions that overlap in broad mass language, the old shorthand loses much of its emotional grip. It stops sounding like common sense. It starts sounding like a provisional habit from an earlier stage of the field. That is the right place to return to the central question, because the case has now earned the strongest wording the evidence can honestly support. HR 8799 is useful first because it taught the field to take directly imaged giant planet atmospheres seriously. Long before JWST, that system already occupied a special place in exoplanet science, because several companions could be seen directly in one architecture. What later spectroscopy added was the realization that the atmospheres were not merely cloudy decorations around glowing young planets. They were chemically informative. In the new JWST era, the 4 to 5 micron window sharpened that lesson. Carbon-bearing molecules became part of a comparative language about enrichment and formation, rather than a side note for atmospheric specialists. That comparison matters for 29 Cygni b because it places the chemistry in an empirical lineage. The enrichment signal is not a one-time interpretive flourish. It sits in a growing pattern in which directly imaged, disk-linked giant companions can show atmospheric behavior different from what one would expect of simple stellar composition inheritance. The exact masses, temperatures, and architectures differ, but the methodological point is the same. Atmospheres are now discriminating tools. HD 19467b is useful for the opposite reason. It demonstrates that the same observational machinery does not automatically deliver a planet-like verdict. The same wavelength range can illuminate a companion whose chemistry sits more comfortably with a brown dwarf or stellar-like interpretation. That is crucial because otherwise a skeptic could say the method is biased, that once you hand observers a JWST spectrum, they will inevitably talk themselves into disk enrichment. The comparison says no, the method can distinguish. It does not merely flatter one hypothesis. Beta Pictoris b plays a smaller but still valuable role. It reminds us that the argument between mass and formation history did not begin with 29 Cygni b. Very massive planets around young bright stars have been challenging public intuition for years. Beta Pictoris b is not identical to 29 Cygni b in age, orbit, or evidentiary stack, and it would be a mistake to merge the two stories, but it does help establish that high mass alone was already a weakening guide. The field had warning signs. 29 Cygni b simply brings several of them into unusually sharp focus at once. These comparisons also teach restraint. Not every massive directly imaged companion with an interesting spectrum should be narrated as if it has rewritten the boundary problem. Some serve mainly as methodological stepping stones. Some are cleaner brown dwarf benchmarks. Some remain ambiguous. 29 Cygni b stands out, not because it abolishes that diversity, but because it sits at one of the most symbolically loaded masses, while still being chemically and geometrically legible. It is the place where the public shortcut most expects to win, and the evidence most clearly refuses to let it. There is a second comparison lesson that matters for the broader taxonomy question. Similar masses do not guarantee similar biographies. That may sound obvious once stated, but much of the public confusion around planets and brown dwarfs comes from treating mass overlap as if it were a classification scandal. It is not. Mass overlap is what naturally happens when multiple formation channels occupy neighboring territory. The real task is to identify which clues separate those channels after the overlap has occurred. Comparative chemistry is becoming one of those clues. Another reason the comparison lane matters is that it protects the documentary from overfitting one object. If 29 Cygni b were discussed entirely alone, a cautious viewer might wonder whether the interpretation rests too heavily on idiosyncrasies of one system. Brief comparisons answer that concern without letting the film dissolve into a survey. The chemistry lane exists elsewhere. The contrast lane exists elsewhere. The tension between mass and origin exists elsewhere. What is special here is not that the themes are unique, but that they converge in one exceptionally revealing companion. The comparisons also show how categories in astronomy usually change. They are not replaced overnight by a single conference declaration. They are eroded by accumulating cases that expose mismatch between the old labels and the newer evidence. One object shows the line wobbling, another shows that chemistry matters. Another reveals that similar masses diverge in origin-sensitive ways. Eventually, the community stops trusting the old simplification as much as it once did. 29 Cygni b belongs to that cumulative process. It is a particularly clear example in a longer scientific correction. That is why it would be wrong to frame the object as an isolated loophole. Loopholes leave the main rule intact and simply slip around it. 29 Cygni b does not do that. It demonstrates that the rule was answering the wrong high-level question. Once the question becomes formation rather than thermodynamic regime, the comparison objects make clear that the field already has the tools, imperfect but improving, to sort similar masses into different historical stories. That methodological shift is the real value of comparison cases. They teach the viewer that astronomy is not replacing one dogma with another. It is learning how to discriminate among superficially similar objects with better tools. A decade ago, several of these companions would have shared the same public label, mostly because the field lacked the evidence to do much better. Now similar-looking cases can begin to separate. That is progress, even when the vocabulary lags behind. If mass is not enough, what kind of object is 29 Cygni b actually? Under current evidence, the best answer is that 29 Cygni b is a planet-like companion formed within a protoplanetary disk. That is the narrow verdict. It is not a slogan, it is a ranking of explanations. The chemistry points that way because the atmosphere appears enriched in heavy elements relative to the host star, with a metallicity ratio reported around 3 ± 2 and a heavy element inventory on the order of 150 Earth masses. The geometry points the same way because the spin-orbit difference of about 12 ± 6 degrees remains consistent with alignment. The architecture points there too, through a low mass ratio around 0.008 to 0.01 and a moderate orbital separation around 17 astronomical units. The mass places the companion in the disputed zone, but the rest of the file explains how to read that zone. This matters because the old shorthand has not simply become less fashionable. It has lost its right to behave like a verdict. Deuterium burning remains real physics. Around the threshold, the object's interior can enter a regime genuinely different from that of lower mass giants. But a thermodynamic regime is not the same thing as an origin category. That distinction is the heart of the entire story. It is also why the broader boundary problem remains unresolved. Saying that 29 Cygni b is best interpreted as disk-built does not mean every object near or above the deuterium burning line should receive the same reading. Different systems preserve different clues. Some companions may fit cloud fragmentation better. Some may remain genuinely ambiguous. The borderland is real, because nature allows multiple routes to converge in mass. That is the deeper answer to where planets end. They do not end at one universally stable public number. They end where the evidence for planet-like formation stops being the best explanation. In some systems that may happen below 13 Jupiter masses. In others it may happen above it. The old rule survives as a shorthand for a physical regime, not as a final authority on identity. This is also why the story stayed locked on one case file. A general lecture about planets and brown dwarfs could easily become abstract and slippery. 29 Cygni b keeps the question honest. Here is one object. Here are its measured clues. Here are the rival histories. Which history survives best? Once the question is posed that way, the answer becomes clearer than public taxonomy usually allows. There is something quietly important in that. Categories often feel weakest at the exact moment evidence becomes strongest. The more data we gather on border objects, the more often we discover that the edge was never a line at all. It was an overlap zone that looked like a line only from far away. That is what 29 Cygni b exposes so well. It is not most interesting because it is huge, or because it almost sounds like a failed star, or because it can be marketed as a record holder. It is interesting because it shows the moment when mass stops being enough and formation evidence has to take over, and that is where certainty also ends. We have a strong verdict on this object. We do not have a universal solution to the taxonomy problem. The object narrows the case. It does not erase the overlap regime for everything else. That balance matters. If the story ended by pretending the whole borderland had become simple, it would betray the evidence. If it ended by saying nothing useful had been learned, it would also betray the evidence. The honest middle ground is stronger than either extreme. There is one final reason that middle ground deserves emphasis. Scientific maturity often looks disappointingly modest from the outside. People want one word, one bin, one line, but some of the most important progress in astronomy comes when the field learns that its categories were too blunt and that better questions have to replace them. 29 Cygni b is valuable because it forces exactly that replacement. The old question was, is the mass above or below a public threshold? The better question is, what does the best available evidence say about origin? Once that replacement happens, the companion becomes much easier to read. The chemistry is no longer an optional detail. The geometry is no longer background scenery. The low mass ratio is no longer an oddity. Each clue becomes part of a single answer. 29 Cygni b is best interpreted as a disk-built, planet-like companion. The wider boundary between planets and brown dwarfs remains a region of overlap where similar masses can emerge from different pathways. That is where the science is strongest, not at the comfort of a simple label, but at the discipline of reading the clues that still preserve origin after the easy shortcut has failed. There is an important philosophical shift buried inside that answer. For decades, classification at the planet brown dwarf boundary was often treated as if astronomy's job were to discover the correct line already present in nature. Find the right mass, the right burning process, or the right official definition, and the problem disappears. Cases like 29 Cygni b suggest something different. Nature may not offer one universal line because the relevant populations overlap in the space of observable properties. If that is true, then the job of science is not to worship a border, it is to infer histories from incomplete evidence as honestly as possible. That sounds less satisfying than a single number, but it is actually a more mature picture of how astronomy works. We classify stars, planets, brown dwarfs, and galaxies not because the universe is obliged to deliver perfect bins, but because categories help us reason about populations and mechanisms. When a category stops matching the mechanisms well, the category has to loosen or be demoted. The deuterium burning rule is now in that position, useful for some bookkeeping, too blunt for final identity. This does not mean words have become meaningless. Planet still points, in the strongest scientific sense, toward bodies whose best supported origin lies in a circumstellar disk, and whose architecture, chemistry, and system context fit that reading. Brown dwarf still points toward a substellar population, often understood through interior physics and more star-like formation pathways. The trouble comes only when one use of the words mass shorthand is mistaken for all the others. 29 Cygni b exposes that mistake, because its interior regime and its best supported origin do not line up cleanly with the public expectation. There is also a lesson here about uncertainty. People often imagine uncertainty as the state that exists before enough data arrive. In boundary problems, uncertainty can persist even after the data become rich, because the universe is not arranging itself around our taxonomies. Rich evidence can sharpen a narrow verdict on one object while leaving the wider category border fundamentally overlapping. That is not failure. It is what success looks like when the underlying populations genuinely intersect. The object, therefore, answers the opening promise in two layers. The narrow answer is that 29 Cygni b is best interpreted as a disk-built, planet-like companion. The wider answer is that where planets end and brown dwarfs begin cannot be reduced to one public number, because similar masses can emerge from different pathways under different environmental conditions. Both answers matter. One is about this system, the other is about how to think. There is something valuable in the modesty of that conclusion. Astronomy often earns public attention through simplification. One line, one threshold, one record, one headline. But the deeper reward of the science usually arrives later, when the simplification breaks and the real structure of the problem comes into view. 29 Cygni b is a reward of that second kind. It teaches us not merely that an object near 15 Jupiter masses can still be planet-like, but that origin-sensitive evidence has now become strong enough to outrank inherited shorthand. That is also why the case should not be sold as a victory lap for one side of a semantic argument. The most interesting outcome is not that one camp gets to claim the word planet. The most interesting outcome is that the field is learning which clues remain trustworthy in a region where categories overlap. Chemistry, geometry, host star context, and architecture now have to be read together. Once they are, the answer gets both stronger and more conditional at the same time. Stronger for the object in hand, more conditional for the universal border. In practical terms, that means the future of this boundary question will likely come from more objects that can be characterized the same way, more systems with dynamical masses, more atmospheres observed in the chemistry-sensitive infrared, more host stars with geometry constrained well enough to compare against companion orbits, more population studies that separate low-Q disk-linked companions from miniature binaries instead of treating them as one blur. 29 Cygni b is not the end of that work. It is a demonstration of what the work looks like when enough evidence finally lines up. So where do planets end? Under current science, they end not at a memorized public threshold, but at the point where planet-like formation stops being the best supported explanation for a given object. And where does certainty end? It ends where overlapping formation channels produce bodies that share masses but not histories. That is the boundary 29 Cygni b reveals most clearly. Not a line we can point to from far away, but a region we can only understand by reading the clues up close. And that is why the strongest final sentence is not a label, but a method. When mass, chemistry, geometry, and host star context disagree, trust the evidence that still remembers origin. When they converge, let that convergence outrank the shortcut. 29 Cygni b gives us that luxury. Few border objects have, at least not yet. If mass is not enough, what kind of object is 29 Cygni b actually? The best present answer is that it is a disk-built, planet-like companion living inside a mass range that public language long treated as brown dwarf territory. That answer is stronger than a guess because it does not rest on one line of evidence. It rests on a stack that keeps pointing in the same direction. The companion's estimated mass places it in the disputed regime near the famous deuterium burning threshold. Its companion-to-star mass ratio remains low, around 0.008 to 0.01. Its atmosphere appears enriched in heavy elements relative to the host star, with a reported metallicity ratio of about 3 ± 2 and a heavy element inventory on the order of 150 Earth masses. Its orbit remains broadly consistent with disk-linked alignment, with a spin-orbit difference around 12 ± 6 degrees. None of those clues alone settles the case. Together, they change which interpretation is most defensible. That is also why the old 13 Jupiter mass rule survives in memory but fails as a final answer. The rule points to real physics. Deuterium burning is not imaginary. Under the right interior conditions, that process does begin in this broad mass regime. But thermodynamic behavior is not the same thing as formation history. A deuterium burning threshold can tell us what an interior may do. It cannot by itself tell us how the object came to exist. Once that distinction is clear, the whole argument around 29 Cygni b becomes easier to follow. The companion is not forcing astronomers to abandon categories altogether. It is forcing them to rank evidence more carefully. Mass matters. It just matters less than people thought when the question is identity rather than interior physics. That is the broader payoff promised at the beginning. The story began with one companion sitting almost exactly where the old shortcut sounded strongest. It ends with a more disciplined picture of the boundary itself. Planets and brown dwarfs do not divide along one clean public number. Their histories can overlap in mass even when their origins differ. The famous threshold still identifies a meaningful physical regime, but it no longer deserves to dominate the whole classification story. So the answer is not that 29 Cygni b solved the taxonomy problem once and for all. It did something more useful. It showed unusually clearly how the taxonomy problem has to be approached. Start with the object. Separate evidence from interpretation. Ask which clues still preserve origin once mass has stopped being decisive. Then accept the strongest narrow verdict without pretending the entire borderland has become simple. That is where the case leads under current evidence. 29 Cygni b is best interpreted as a planet-like object formed within a protoplanetary disk, and where planets end, in the broader sense, remains a region of overlap, where nature refuses to compress itself into one clean line. There is a quiet kind of relief in that answer, not because the border has finally become simple, but because the evidence tells us what kind of simplicity to stop demanding. 29 Cygni b does not ask us to abandon rigor. It asks us to apply rigor to the right question, not what number makes us comfortable, but what history best fits the clues that survived. That is probably how this boundary will keep changing. Not through one dramatic renaming exercise, but through more systems that can be examined at the level 29 Cygni b now has been. More dynamical masses, more chemically informative spectra, more host star geometry, more comparisons between low mass ratio companions and the populations they do or do not resemble. As that evidence grows, the old shorthand will likely remain useful as a rough marker of an interior regime, while losing more and more of its authority as a final identity label. That is enough to answer the case honestly. Strong verdict on the object. No fake closure on the whole borderland. In science, that is often the cleanest ending available, and here it is more than enough. And that may be the most useful thing 29 Cygni b offers. It does not simplify the universe. It shows us where we were simplifying it too early. The line survives as a clue. The case survives as a better answer. That is the boundary lesson, and the reason this object matters. It teaches precision where the shortcut taught confidence, and that is enough, for now.